Let's jump right into this explainer. Today we're talking about the Earth's absolute biggest, most untapped battery, the ocean. You know, whenever we talk about renewables, the conversation almost inevitably goes straight to solar panels and wind turbines, right? But covering over 70% of our planet is this relentlessly powerful, astonishingly dense source of energy. It's constantly moving, constantly soaking up the sun's heat. It's literally an engineer's dream. And, as we'll see, an absolute nightmare of a challenge. Just look at this number, 1.5 million megawatts. And get this, that staggering figure is just the estimated recoverable power from the tides alone. That doesn't even factor in the endless crashing of waves or the massive amount of thermal heat locked up in tropical waters. The raw scale of what the ocean has to offer is honestly kind of hard to wrap your head around. It's this epic reservoir of power, literally just waiting right off our coastlines. So how do we actually tap into it? Well, to wrap our heads around this free energy, we're going to break this explainer down into 4 parts. The ocean energy giant, ocean thermal energy, power from the waves, and finally, tapping into the tides. Let's get to it. Part 1, the ocean energy giant. Think of this as a massive, free battery. To really get this, we have to stop looking at the ocean as just a bunch of water. It's a colossal repository of energy. You've got thermal energy from direct solar heating, mostly near the equator. And at the exact same time, you've got massive amounts of mechanical energy, both kinetic and potential, whipping around out there, driven by the wind, the rotation of the Earth, and the gravity of the moon and sun. But here is the ultimate catch. The central paradox of ocean energy is exactly this. The fuel is completely free. We don't have to mine it, we don't have to pipe it, we don't have to burn it. But building machines tough enough to survive the ocean, that requires some gargantuan capital investment. The sea does not give up its power easily, folks. Your equipment has to be incredibly durable to survive brutal saltwater corrosion, violent storms, and the sheer relentless pounding of the waves day in and day out. All right, moving right along to part 2, ocean thermal energy. This is where we start treating the ocean like a giant heat engine. This is a brilliant concept known as OTEC, but it is pretty picky about geography. It really only works in tropical or equatorial climates. Why? Because you need the sun to heat that surface water up to a nice, balmy 28 degrees Celsius, while a kilometer down, the deep water is sitting at nearly freezing, around 4 degrees. And in the world of thermodynamics, anytime you have a hot source and a cold sink like that, you can drive a power cycle. Nature is basically handing us both. So how do we actually pull the power out? We basically have 2 main ways. On one side, you have open systems, or the Claude cycle. This is wild. You actually pump the warm surface water into a vacuum chamber. Because the pressure is dropped so drastically that 28-degree water literally flash boils into steam to spin a turbine. On the flip side, we have closed systems, or the Anderson cycle. Instead of boiling the seawater itself, it uses the warm water to vaporize a separate fluid with a really low boiling point inside a closed loop, like propane. In both setups, you then pump up that freezing deep water to cool the vapor back down into a liquid, and the whole shebang starts over. But, and this is a massive but, there is a huge hurdle here. Physics kind of gets in the way. Because the temperature gap between the surface and the deep water is only about 24 degrees, the absolute max theoretical efficiency, the Carnot efficiency, is incredibly low, just 8%, and that is strictly theoretical. In the real world, actual OTEC plants achieve a mere 3% efficiency. Once you burn energy just pumping that freezing water up from a kilometer deep, your net power gets really, really tight. And that 3% efficiency has some very real, very physical consequences. Because you're working with low-temperature steam, it takes up a ton of volume, so the equipment has to be staggeringly huge. Just to get 1 single megawatt of power, your heat exchanger needs 4,400 square meters of surface area. To put that into perspective, the steam in this open system is so expanded it takes up nearly 86 cubic meters per kilogram. A traditional fossil fuel plant, that highly pressurized steam is a tiny fraction of the size, at only 0.033 cubic meters. So OTEC needs massive turbines and huge infrastructure, which makes it wildly expensive to build for the electricity you actually get out of it. Okay, part 3, power from the waves. Now we're shifting from temperature differences to the raw, kinetic motion you can actually see and feel. Think about this. On average, around 3 million waves break onto a coastline every single year. 3 million. And a traveling ocean wave is basically a perfect little package of physics. It holds identical amounts of kinetic energy from the water physically moving and potential energy from the water being lifted above sea level. So, skipping all the dense hydrodynamics, the main takeaway here is just the sheer density of that moving water. It offers phenomenal power generation, if we can just figure out how to catch it. And one of the cleverest workarounds engineers have come up with is oscillating water column technology. It works like this. A wave rolls in and pushes a column of water up inside a hollow, partially submerged chamber. That water acts like a giant natural piston, compressing the air trapped above it and blasting it out past a turbine. When the wave recedes, it literally sucks air back in. The system basically breathes. And the really genius part? They use a specialized rotor geometry so the turbine blades spin the exact same way whether the air is rushing out or rushing in. That means no moving valves to break down in that harsh salt water. Now, when it comes to setting these plants up, they generally fall into 3 coastal buckets: shoreline, near shore, and breakwater. And breakwater plants are turning out to be uniquely cost-effective. By building the wave turbines right into existing municipal harbor walls or coastal protections, like the commercial plant operating in Matricu in Spain, you basically split the massive construction bill with the local city. They get a barrier that protects the harbor, and we get electricity at the same time. Talk about a win-win. But if we head further offshore, the designs get pretty wild. Take the Pelamis wave energy converter. Imagine a 150-meter-long mechanical snake made of 5 massive steel tubes floating just barely submerged in the deep water. As waves roll by, they force these heavy tube sections to flex and bend at their hinge joints. The system uses that immense bending force to drive hydraulic cylinders. Those cylinders resist the wave motion, continuously pumping fluid into high-pressure accumulators to spin generators. One of these standard machines can crank out up to 750 kilowatts of power. Another really cool offshore concept is the WaveStar prototype over in Denmark. The test unit you see here operates with 2 floats that basically ride the passing waves to push hydraulic arms up and down. But try to picture the full commercial version. They want to string together 20 of these massive hydraulic arms, 10 on each side, capturing energy sequentially like a giant zipper as a wave rolls down its length. Oh, and if a crazy storm hits, the system is designed to literally pull the floats entirely out of the water to save itself from being ripped apart. All right, which brings us to our 4th and final section, tapping into the tides, where we put lunar gravity to work. This is arguably the most predictable renewable energy on the planet. Because tides are literally driven by celestial mechanics, they run on a super reliable 29.5-day lunar schedule. You can set your watch by it. When the Earth, Moon, and Sun line up perfectly during a full or new moon, we get what are called spring tides. That gives us our absolute maximum tidal range and the most energy. On the flip side, during quarter moons, their gravitational poles kind of fight each other, giving us much smaller neap tides. Because this cycle is so perfectly predictable, we can forecast our exact power output days, months, or literally years in advance. And here's the thing about tidal energy. It's not science fiction. It is a proven asset. It acts a whole lot like a traditional river hydroelectric dam, just using the ocean's potential energy as the tide swings in and goes out. Now, you do need specific geographic spots with massive tidal ranges to make it work, places like the Bay of Fundy or the coast of France. Actually, the massive Rance facility in France proves this perfectly. It was built back in 1967, and it's been reliably spinning its 24 identical turbines ever since, cranking out 240 megawatts. There is a really fascinating operational quirk with these tidal dams, though. When the tide goes out, you trap a gigantic pool of water behind the dam. Mathematically, to get the absolute maximum power, you'd want to just rip open the floodgates and drain it instantly. But engineers don't do that. Instead, they use what's called a modulated single-pull system. Basically, they let the water out slowly over several hours. Why? Because dumping it all at once would send a violent, massive spike of electricity that would completely overwhelm the local power grid. So they modulate it, sacrificing a little bit of total theoretical energy to get a nice, steady, manageable flow of continuous electricity. So to wrap up this explainer, I want to leave you with this final thought. Think about what we've covered today. We have massive thermal gradients in the tropics, millions of waves endlessly crashing against our shores, and the perfect gravitational clockwork of the tides. The ocean is literally an infinite free mechanical battery beating against our coasts every single day. We know the engineering works, so the ultimate question is, how much capital are we willing to invest, and how many massive structures are we willing to build to finally unleash this giant? Thanks for exploring this fascinating topic with me.